Okay, so hi there, everyone. In this video, we're going to discuss about conditional probability. This is the next topic right after the basic approach to probability. You should have watched videos on the approaches to probability, the probability of events, and that will include the additive rules, with mutually exclusive, with the concept of mutual exclusivity and non-mutual exclusivity. So with that in mind, we will continue with this, what we call conditional probability here. So start. So our lesson objective for this one will be at the end of the lesson, you can define conditional probability and apply it in real life situations. Let's consider this one table where it involves the examination of a large number of insurance claims, categorized according to the type of insurance and according to whether the claim was fraudulent. The examination produce the results shown in the following table, wherein you can see the fraudulent claims F here and non-fraudulent claims. So when you say fraudulent, so it's a fraud claim. It's not really true that you got in an accident or something. And when you say non-fraudulent, it's a true claim. So we have types of insurances: fire policy, automobile policy, and others, wherein it totals to 100%. So to show you an example of a fraudulent claim here, one is a common GIF found in the internet. So you can see this man over here. He wants to get this insurance, maybe accident insurance or something, and he ended up doing things like that. Okay, so suppose you are a checker for insurance claims and you want to check for the fraudulent claims to be exact. And from the table that was given a while ago, we want to ask what's the probability that it will be fraudulent. So note that there are additional information in the table. It's not only about fraudulent or non-fraudulent claims. It also has the type of policy in it. And suppose that a claim that you're examining is a fire policy. What is the probability that it is fraudulent? So these kinds of questions or these kinds of situations here can be answered by what we call conditional probability. Okay, so let's start with this. We will let this variable f, this event f rather, to be the claim is fraudulent, which starts with f. We wish to find the probability that probability of f, given that it is a fire insurance. So in symbols, we will write it like this. So p, the probability of f given e. So that's how we read it. This is how we write it. It's not a slant, but it's a straight vertical line. Hence, conditional probability involves finding the probability of an event given that there is another circumstance or another event have already occurred. If we will not use conditional probability in this manner, it will tell us that we are actually involving all the types of claims in this situation. So it may be fire, auto, or others. This is what we call unconditional probability or marginal probability. It will be 1/10 to be exact, because going back from the table, if it's only fraudulent and there's no given, or there's no such thing as determining what claim it is, it's going to be 10 divided by 100. So that's 1/10. And that's what we call marginal or unconditional probability of that event F. So however, since we have additional information that we are actually looking at the fire policy, well, we can determine the probability of event F using such information, basing on that sample space. And our probability assessment would be more realistic. So let's define conditional probability before we answer that. Consider two events A and B with non-zero probabilities of both A and B, because if there's one, we won't be continuing in this definition. The conditional probability of event A, given that event B already occurred prior to A, is P, probability of A given B, is equal to their intersection divided by the probability of the given event, or the event that already occurred. Likewise, the conditional probability of event B, given that event A has already occurred, is the probability of B given A is equal to their intersection divided by the probability of A. Note that conditional probability is not commutative. So notice here that in these two conditional probabilities, A given B and B given A, the denominator changed, right? Um, Intersections are commutative as well as unions are commutative or joins are commutative, but conditional probabilities are not commutative. Okay, we also know that set differences are not commutative. So we should also put in mind what the condition is before solving for such probabilities. The probabilities of one event, say, be occurring when it is known that some event already occurred. So we're going to, shall we say, we are going to respect the occurrence of such event because it will alter the events or the probabilities of the next events that will occur. So in short, conditional probability restricts the sample space. It's not going to be respecting the overall sample space S, but it will have a new stricter sample space, which is the given event that already occurred. So we denote that obviously by this because we already shown that this is read as the probability that event B occurs given that event A occurs, or let's make it simple, the probability of B given A. That's it, knowing that they're events. So let's put this in consideration. Say we consider the experiment of tossing a die. Let event B be getting a perfect square. We know perfect squares as numbers wherein if we're going to get a square root or the root of them, it's going to give us an integer. Okay, right? Like 9 square root of 9 is 3, like 16 square root of 16 is 4. And of course, in this example, we have let's consider B to be getting the perfect square. So we find the values here, the probability of odd numbers. We know odd numbers is 1, 3, 5 in this scenario. So the probability of getting an odd number is 3/5, or 3/6 rather. It's going to be 3/6. So I'm going to type it down. 3/6. That's for odd number. The probability of even numbers is we have also 3 even numbers, so 3/6. Of course, for probabilities, as much as possible, we will simplify them into 1/2. This one will also be 1/2. Okay, so that's the answer for odd and even number. For the B, remember that B is a perfect square. How many perfect squares we have here? And yeah, bingo, we have 1 and 5. So 1 is a perfect square. Square root of 1 is 1. Sorry, not 5, 4 rather. Square root of 4 is 2. Okay, so we have 1 and 4. So that's gonna give us 2/6. Simplify that thing, we have 1/3. So these are the answers for our number. Okay, let's proceed to the next slide. Okay, let me clear this up. Next, suppose it is known that the toss of the die resulted in a number greater than 3. So for example, it's a biased die. It's an uneven die that it will prefer to land on numbers greater than 3. So we know numbers greater than 3 on that die. We have 4, 5, 6, which is a subset of the sample space. To find probability of B occurring, B is a perfect square again, relative to the space A that we have. We must first assign probabilities to the elements of A proportional to their original probabilities such that their sum is equal to 1. The sum is equal to 1 for all probabilities, right? So it should not be, because if you're going to distribute the probabilities, it should all go back to 1. Okay, so take note of this. So what's the probability of getting an odd number given that A occurred? So we are sure that a number greater than 3 will occur. So in this new sample space, we're going to know that the odd numbers. So obviously, we already have 1 there, which is 5. So therefore, what we have is 1/3. For the even numbers, we have 4 and 6 in this reduced sample space A with numbers greater than 3. So what we have is 2/3. Notice that if we're going to add 1/3 and 2/3, it will give us 3/3 or 1. And that should be that should be the thing. Okay, clicking next and clear that up. So relative to space A of the event that more than 3 will occur, we find that B contains a single element, which is 4. Remember that B is a perfect square, A is a number greater than 3. So if we're going to have this B, probability B given A, denoted by this symbol. Sorry, should not be slanted. It's italicized or something. It should be like this. So we write B given A is only 4 because there's only one perfect square in that reduced sample space, 4, 5, 6. So that's 4. And hence, the probability of B given A, since there's only one, that will be 1 over 3. Okay? That's 1 over 3. So we'll continue in this manner. Let's go back to this example here. And I try to answer some problems. Let me clear this up. Problems regarding conditional probability. And usually the problems that conditional probability is part of, it can be written in a table like this, which makes the visuals pretty much easier compared to the just analysis, especially for those visual ones like you. Refer to the insurance claims data above and find the probabilities of the probability that the claim is fraudulent given that it involves an auto policy. Now, again, if it involves an auto policy, we are actually just reducing the sample space into the auto policy because we have the word given here, given that it involves the auto policy. So if that's the case, we're only restricting ourselves with the auto policy here. We're not going to respect the whole sample space up to 100%, but it's only going to be here, which is 30%. So if we want to find the probability that a claim is fraudulent and that it involves an auto policy, we just need to highlight fraudulent here, which is the intersection of F and A. Notice here, intersection of F and A, which is our numerator. So let me write it down. That's 1%, or maybe we can just hide the unit for now. 1% divided by the probability of the given event. Our given event is the auto policy, right? So it's going to be 30. So the probability that a claim is fraudulent given that it involves an auto policy is 1 over 30. Okay, now let's try to answer letter B. Determine the probability that the claim is non-fraudulent given that it is a fire policy. So fire policies, this is the given. So we're going to highlight ourselves to the fire policies this time. We're gonna forget all the others there. And let me erase all the things that we don't need for now. Okay. Oops, sorry, my bad. Okay. Given that it involves a fire policy, so we have highlighted already the fire policy, and we want to know the probability that it is non-fraudulent. So non-fraudulent is F complement. We're going to highlight this intersection of the E and the F complement. That's going to give us 14. So that's our answer. That's our numerator, the intersection 14 divided by the overall number here, which is 20. And of course, we can simplify this into what? Divide them by 2, 7 over 10. Okay. So that's the answer for letter C over there. Let's proceed to letter C. Find the probability that the claim is fraudulent find the probability that a claim is fraudulent that it does not involve a fire or auto policy. So it does not involve a fire or auto policy. So it should be, the others. That's our given. We will need to find the probability that is fraudulent. So F is here. So if we're going to highlight the F, here it is. So where do they intersect? This is another point of view for some. So we have here their intersection is 3. So we're going to write that down as the numerator, 3, divided by the others. So that's going to give us 50. So that's the answer, 3 over 50. Simplify if needed, but we cannot. 3 is a prime number. So that's our answer for letter C. And lastly, let's try to answer letter D here. Find the probability that an auto policy is non-fraudulent. Okay, so the probability that we are concerned with is actually the non-fraudulent here. It's like it's it's constructed differently. The probability that an auto policy is fraudulent. So you should be very careful in determining the given event and what is the event that we want to find the probability with. In this sentence, if you're going to read it again and slowly this time, find the probability that an auto policy is non-fraudulent. So it's given that it is an auto policy, and we want to find the probability that it is fraudulent. So it's going to be 29 over 30, and that is our answer for letter D here, 29 over 30. And that's it for this example number 2. Okay, so I guess I will end this video right here for now. We will be seeing more examples in the next few videos, and we'll be encountering the next parts, which involves independent events, and of course, eventually we will reach the probability distributions right after. So thank you very much, and see you in the next video.